Okay, now that we're finished with the overview of the entire storm drain system and your documentation, let's look at these individual data sets. So first off, if we go back to our storm drain documentation, what we want to do is get to, let's see, if I hit create a storm drain, I can do create a storm drain from shapefiles, and this has, let's see, points. Yeah, this has these individual layers. Create a storm drain from shapefiles, and then let's go down a little bit just so that we can open up this guy right here. And so in this system we have this, I'm going to call these templates, these storm drain templates that you can use to learn how to build a storm drain network. Okay, so points, nodes, are points files, points layers, and they have attributes. And polylines, links are polyline layers, and again they have attributes. So nodes are inlets and junctions, outfalls, and storage units. And polylines are like links, conduits, pumps, orifice, and weirs. And the following data, let's see, okay, so external shapefiles, let's go ahead and do this. So we're going to start, we did this where we imported this L3, lesson 3, into the grid, and then we're going to review all of these data from these. So let's start with inlets and junctions in this video, because inlets and junctions are probably the most comprehensive topic that we have. So this is a point layer that contains inlets, nodes, manholes, and junctions. This figure is going to show the fields that are used for the storm drain modeling. So for every inlet or junction that you have, an inlet, manhole, or junction that you have, you need a name, an inlet type, elevation, max depth. I'm not going to go over the not required ones. Length, width, length or perimeter, width or area, height or sag or surcharge. This kind of depends on, these three variables right here depend on this type. If this type is 0, 1, 2, 3, or 5, 2, 3, 4, or 5, then you will have different, these options will vary. Okay, weir coefficient, feature, curb height, clogging factor, time for clogging, drop box area. So if they're not required, that means that you can leave them null or you don't have to assign them. Let's see what these numbers are here too. The ponded variable is not used. Oh, right. I think I took the ponded out. We don't use the ponded variable for Flow 2D but you may need a ponded variable in the INP, but we don't use it. So you can either export that variable, should be exported as either 0 or null. Okay, so here we go, inlet. So let's go ahead and open this. So the first thing I'll do is I will close these windows, and then we right click inlets and junctions, open attribute table, and then let's dock it. This is the docking button right here. That way we don't have to hide, the window won't be hidden when we want to do something with QGIS. Alright, so I'm going to zoom up in here, and I think what I can do is, I don't know, that image is kind of distracting. Let me try doing just Google Satellite. Yeah, that's better. Now I don't have those labels that are distracting. All right, and what I want to do is sort this by type so that you can see the different types. So let's first of all, before we get too far ahead, let me go here to right here, and what we are looking for is, let's see, chapter 2, storm drain features, inlet types. Okay, here are the different inlet types. We have type 0 is a junction, meaning that it does not interface with the grid. Type 1 is a curb opening, 2 is a curb opening with gutter, 3 is a grate, 4 is a unique, like a head wall, and 5 is a manhole. These features interface with the grid to either receive or flow into their feature, or to return flow back to the feature if the swim system is over capacity and it can flow back out onto the grid. So that is the purpose of these inlet types. And then the secondary node type in here is a junction. So if the type is 0, then the node is a junction, and you can see all it requires is an invert elevation and a max depth, and all the other variables Sorry, that one you can ignore. That should be 0. Okay, and let's see. So if we zoom in on one of these, let's just grab one down here and click zoom to feature, and this is a T, and then this one is probably a manhole. So now if you wanted to color these by type, you could certainly do that just by changing the this to category and putting the category to type, and then classify, and then uncheck that because there won't be any, and click apply and OK. And now you can see that they are colored by their inlet type. So if they are a junction, that would be dark blue. Let me unselect that feature so that you can see that that is dark blue. And if they are a type 3, that would be a grate, that would be green. All right, so let's go over these types starting from 1. So here is, and then as you can see, I've sorted this by type just by clicking that column. And now we can go down to the type 1s. And okay, here we go. Here's some type 1s. So type 1. Now the thing about any other inlet that's not a junction needs to start, its name needs to start with the letter I, and that can be either a capital letter or a lowercase letter. Type 1 is a, let's go ahead and back to the document. Type 1 is a curb opening with the inlet at grade, meaning no sag. It needs a length, a height, and a weir coefficient as the mandatory variables. All right, so let's take a look at one of these. Let's try this one. We'll click select it and then zoom to the layer. Let's try a different one. Let's get one that actually resembles a curb and gutter. That one's probably supposed to be like right here or something. I don't know. It's hard to say. Let's grab another one. Let's go ahead and zoom to this one. Oh yeah, that's better. Okay, excellent. Yeah, this is perfect. Okay, so you can see here that this is a curbside inlet, and you can kind of see that it doesn't have a grate down there, so it's probably a curb opening. All right, so what do we need with a curb type 1? We need an invert elevation that would represent the bottom of this node. So it'd be basically the bottom of the catch basin box. And then a height, which would be the difference of the grid element elevation to the bottom of that box. And there's a calculator. This calculator here can fill that data, but it can't fill it on the shapefiles. It has to fill it on these layers here, so we can't use it right now. So that would be the max depth from the surface to the bottom of that node is 4.5 feet. You don't need an initial depth or surcharge depth for these. You wouldn't use a surcharge depth on a type 1 because those are more of a manhole thing. And you would only use an initial depth if that was already partially full, like say it was in Florida or something. Okay, here's the length, meaning that the curb opening is 10 feet long. And the width and area is, the length perimeter. So for type 1, it's a length. And for type 1, it's a width. Type 1s don't have a width because, let me show you why. Because there is no sag, there is no curve opening sag right here. Okay, so they don't have that extra width. And let's get back here. Sorry. And now they do have a height, which is 0.42. That would be the curb opening. And all these dimensions are in feet, and then of course a weir coefficient. All right, and then they do not have to have, but they could have a curb height, a clogging factor, a clog time, and a drop box area. So if our standard drop box area is like 4 by 4, I think, and that would like help you determine the volume of the drop box. But if you have a really oddly shaped drop box, you can define the drop box area. We have a clogging factor and a clogging time. So the clogging factor would be a percentage, like 0.5 or 0.8 or something like that. And it would just be a factor multiplied by the area of, the dimensions of the inlet, and then the clogging time would be when that clogging started. And so this would be hours. This is a factor, and yeah, that's it. Okay, let's go ahead and go down to the next one. We'll go to I2. So here is a I2, a type 2 inlet, and we'll go ahead and zoom to that. And let's get a better one. That one's, yeah, that one's probably is right there, but let's try a different one. Well, that one might be okay. So this one is a type 2, so meaning that it has, let's see, get to type 2. It has a width right here. Now this can also mean that this width right here can also be like a graded opening. Like it could be an opening for the grate. But basically it's got a length, the curb height, and then this width or sag to, like, you know, expand the area so that more water can flow into this structure. And then Noemi has the calculator and how the flow works into this system. So she says all that right here. Okay. What else do we have here? So we do need the invert elevation, just like a type 1, the max depth, just like a type 1. These two, this one's not going to be used on a type 1, 2, 3, or 4, only on a type 5. And I don't even know that we do this. I think we do all of this through this coordinate or this variable instead. Length perimeter right here is 10, and the sag area, or sorry, excuse me, the width area is 1 foot, and the height is 0.42. The weir coefficient is 2.3, and then again we're not using any of these other variables. Whoops, I didn't mean to do that. Okay, so that's 1, that's type 1, that's type 2, and then we have down here type 3. So let's go ahead and zoom in on a good type 3, one that's kind of helpful because they're not all very easy to see. So let's see, zoom. Oh yeah, this is a good one. Nice, we got lucky. Okay, so you can see, you can pretty clearly see that this is a grate. It's a little off. The value or the position is a little off. So when you position these, and if you don't want the position to be off, you want to make sure that, to the best of your ability, we'll get the conduit and the node, and we'll turn on the snapping tool. To the best of your ability, you will try to put the inlet next to its obvious feature. However, as you can see, this feature splits 2 different grid elements, so that's not super helpful. So in that case, what I would do is I would use this tool right here, and I would put it to the lower of the 2 grid elements, and so we wanted to put it to this one. So even though we have put our inlet here, it will actually be assigned to the whole grid element. So the final assignment will be about right here. But if you have it like it splits the difference like this, put it on the lower of the 2 grid elements. Okay, what's next? Whoops, wrong one. Sorry, I meant to go to the next one. Okay, type 3. So invert elevation and the maximum depth. The invert elevation is 1425 and it's 4 feet deep. The length of, or sorry, excuse me, now this is a type 3, so we're not dealing with length anymore, we're dealing with perimeter. So this would be the perimeter of the feature, and then this would be the area of the feature, and then if there's no, and this would be the sag of the feature. So sag meaning that it's a depression, it's depressed within like a radius, and it's like maybe a few inches lower, but of course it'll be measured in feet. So, you know, it might be like 0.1 or 0.05 feet lower than its surrounding, than its neighbor, and that would give it a minor depression. Okay, that's the sag. And the weir coefficient for a grate would be 3. And again, you don't need the clogging factor or the clog time, or the, and this one does have a drop box area, so this one is suggesting that its drop box area is different than a standard drop box area. Okay. And this is just a fake value for me that I just put some in here just to show what the data should look like. Okay, so let's go on then. Let's move. Oh wait, actually I did want to show you that in the book. That's the type 3. Okay, so you get the weir coefficient, a grate, and let's see, a grate perimeter, not including curbside, a grate opening area, and a grate sag. If it's a grade, it's just 0. Okay, that's the grate. Okay, let's move on to a unique type 4. So type 4s are a little bit different. So let me I guess I can, well, we'll just leave that editor on. It really doesn't matter. Okay, let's get down to some type 4s. So we'll start with this first one, which is a big head wall. So let's zoom to this feature. And you can see here that this is a large head wall. I want you to look at, I'm going to click this button right here, and then I'm going to click the grid element, and you see that the elevation here is 1426.2, the elevation here is 1420.3, and the invert elevation of this feature is 1418. Now, because this is a head wall, that means that the invert of the elevation is the elevation at which we want to exchange water with the grid, with the flow 2D grid. So because that's the case, then that means we set the feature switch equal to 1, because we want to start exchanging water with this feature at the invert of the feature, not at the rim of the feature, okay? And the rim of this feature is just essentially the conduit depth. That's what that 4 feet is. This is a 4 feet conduit. Now, I put the location of this inlet node. I didn't put it on this head wall because that was, you know, a pretty large change in elevation. So I put it out here. Now this is what happens when the Flow2D model runs for this type 4. Flow2D is going to scan all of the nodes, and it's going to scan all of the grid elements that the nodes are connected to. And if the grid element elevation is higher or lower than the, in this case it's the invert elevation, but for a type 3 or for a type 1, 2, or 3, it would be the rim elevation. But in this case, because it's a vertical feature, we're going to reassign at runtime the grid element elevation to 1418.8 so that they exchange at the invert of this feature. Okay, so the elevation that you wanted it to be set to this feature, if this is a true head wall at grade, you want that invert elevation to be the grade at which it starts to exchange flow. Now sometimes these head walls, the invert of the node is actually dropped and recessed way down below the invert of the basin. So in those cases, you would want to keep the feature at type, the feature type equal to 0, and then the interface would be at the invert elevation plus the maximum depth, which would be the ground elevation right here. So there are sometimes these nodes are sunk underground, even though they're still a head wall, they're sunk underground. Okay, so that's how the feature switch works for a type 4. And what else do you need for a type 4? So you need invert elevation depth, and you don't need anything else because a rating table or Colvert equation will define the flow into the feature. So for this one, later on in the video when we start adding the data, we'll use a rating table for this one, and then for the rest of these we will use a Colvert equation. So let's go ahead and take a look at these. Let's zoom to this group of type 4s. And these are just smaller type 4 inlets. They're just a 1-foot conduit that connects these type 4 culverts from these tiny little basins into the conduit system. So let's take a quick look at those little basins. Elevation, we need the elevation map. Okay, and you can see here that these little basins will be feeding those type 4s. You can see here there's a little one here and a little one here. So there's 5 of these, I believe, altogether. So I have given them a type 4 and an invert elevation that is basically this grid element elevation at the interface. The maximum depth is the depth of the conduit in the downstream direction, and they don't need any other variables except the feature switch equals to 1, meaning that they interface at the bottom of that node. Okay, let's see that. So that's type 4. Let's go on to type 5. Well, actually, why don't we make sure we showed the type 4 video? Yeah, we did. And this is a type 4 interfacing with a channel. So it still has a feature switch equal to 1, but it interfaces with a channel cross section instead of a grid element or a basin or something like that. All right, let's go with type 5s and let's see if we can find a good type 5. So zoom to layer. Yeah, that one's good. Let's go ahead and turn this elevation off. So you can see that this is our type 5 here. That's our manhole. And what do we need for type 5s? We need in-grid elevation, maximum depth, and this would be the length of, or sorry, excuse me, this is the perimeter of the manhole opening, the area of the manhole opening. This is the height. No, this is the dish. Sorry, this is the surcharge depth for required to pop the manhole, and the weir coefficient. Okay, so manholes work like this. They act as a junction until the cover is popped off. And the cover is popped off when the pressure in the system exceeds the maximum depth plus the surcharge depth plus the water surface depth, or plus the water depth on the node. So once the pressure in the system exceeds those three depths, then the manhole cover can pop off. And when it pops off, it doesn't go back on, it just assumed to be popped off. And after that happens, then the type 5 can then work as an inlet and allow water to flow back into the manhole cover and into the system. Okay, that's type 5s. Let's see if we can get one more bit of information on type 5s. Whoops. Not from here, sorry. We want to get that from here. So this explains what I was just talking about. And if you want to learn how to calculate the manhole cover weight as a head, then you can come in here and use this solution, or you can use this table for estimating some, converting some pressure heads or to feet. Okay, and that is manholes. Let me see. Let me make sure we got everything that I wanted to talk about. So inlets and junctions. So when you set up your shape file, you're going to use, so names are strings. Inlet type is an integer. A real number means it's a decimal number. And your precision can be, 0, 1, 2, or 3. I don't typically go above 3 on this. I usually use just a precision of 2. A feature switch is 0, 1, or 2. And then the rest of these are precision. Okay, and I think that is it for inlets and junctions, so I'll stop this video here.